When I say the word biology, what comes to mind? Maybe cows and horses, chickens, plants, things that you'd see on a farm. Because biology is the study of living things, people and animals and plants. And if I say chemistry, what comes to mind then? Maybe the periodic table? Or a guy in a white lab coat surrounded by glassware and chemicals? Because chemistry is the study of chemical things. It's a natural picture that comes to mind. And how about astronomy? What comes to mind then? Sun, moon, planets? Easy. But what about physics? What comes to mind when I say physics? Or does anything come to mind at all? Because for most people, there is no natural picture that comes to mind for the word physics. Physics 101 is an introduction to the world of physics. But why is physics so difficult to picture? Probably because we can see and handle biology things and chemistry things. Even tiny life forms that are too small to see with our eye, we say, yes, it is life, just like all other life, but just tiny life. And chemistry itself is also familiar and tangible. Even if you aren't a chemist, you know that water is a chemical, and so is the air that you breathe. The idea that chemicals, like water, are made of other chemicals just sort of makes sense. Chemistry is kind of one step below biology. Biology is the study of living things, and living things are made up of chemicals. So, where does physics fit in? Actually, if biology is up here and chemistry is underneath it, then physics fits underneath chemistry and sort of supplies all the foundational laws of the science above it. The foundational laws. And what exactly does that mean? That's probably why it's so difficult to define. It's sort of like saying, think about everything. Physics is just so broad that nothing specific comes to mind. So let's work on this a little bit. A common definition is, physics is the study of matter and energy and the interactions between them. This is also a very common definition for chemistry, which sort of makes sense because they are both so closely related. The universe is often compared to a watch or a clock, and the chemist disassembles the clock into the periodic table of clock parts. Then the chemist reassembles the watch to make different stuff. Now, the physicist is also interested in the watch parts, but that is not his focus. The physicist stands back and looks at the clock or the watch as a whole and asks questions so foundational and in some way so obvious that it might never occur to you to ask those questions in the first place. Like, what is the watch? What is making that little ticking sound? And what mechanism is driving these hands around in a circle? And why a circle? Does it have to be a circle? And what about breaking the watch into individual parts? What if we continue breaking and break the watch parts themselves? Then what do you get? And why does light pass through the glass on the front, but not through the metal on the back? And what is light? In short, how is this watch actually working? There's not an exact clear line between chemistry and physics. There's a lot of overlap. In fact, there's always a little friendly rivalry between the chemistry departments and the physics departments at universities as to just who rules in a particular area of study. The chemistry department says that Their area is a very clear and distinct, separate discipline. The physics department says that chemistry is merely a subset of physics. Even the famous scientist Ernest Rutherford once said, "All science is either physics or stamp collecting." Spoken like a true physicist. And for his efforts, he was awarded the Nobel Prize in chemistry. The two disciplines are so close that people have come up with clever and amusing definitions to illustrate the difference between chemistry and physics. Chemists smash atoms together to see what happens when they stick, molecules. But physicists smash atoms together to see what happens when they break, subatomic particles. Here's another one. If it moves, it's biology. If it changes color or smells funny, it's chemistry. If it doesn't work, it's physics. No doubt that one came from the chemistry department. Here's one. Burning a piece of wood is chemistry. Sawing it in half, that's physics. And here's one that we're going to look at a little closer. The chemist wants everything to be different and is surprised when he finds that everything is the same. The physicist wants everything to be the same and is surprised when everything turns out to be different. What does this mean? You see, the chemist wants everything to be different. That is, he likes the differences, the diversity that he finds in the periodic table of elements, and he wants to combine them to make even more different substances. But if he digs deep enough, he gets into the world of subatomic particles and finds that everything on his periodic table is made up of just a few of the same things, and the differences disappear. But the physicist is looking for those few fundamental laws, the few that make up the whole universe, making everything the same. But the universe stubbornly resists being broken down into this kind of simplicity, and the differences in the universe remain. Thus, the chemist wants everything to be different and is surprised when everything is the same, and the physicist wants everything to be the same and is surprised when everything is different. Here is a pretty good rule of thumb. If it directly relates to the periodic table of the elements, it's probably chemistry. Otherwise, it's probably physics. Copper, aluminum, oxygen, and their possible combinations, these are all on the periodic table. Chemistry. The weights of the elements, the number of protons and electrons, can be found in these numbers here. Chemistry. What makes things hot? Physics. Combining sodium with chlorine. Chemistry. Sound is not on the periodic table. Neither are the laws of motion and electricity, or how hot and cold work. None of these things are directly determined from the information on the periodic table. Thus, they are not chemistry, they are physics. So we see that physics wrestles with a much broader scope than chemistry does, and it forms the foundational laws and ideas for the other sciences. Why is this rock heavy? When I throw the rock, does it slow down or speed up? And why does it fall down? And that noise. What is that noise? It's a splash, I know that, but I mean, what exactly causes it? And the waves. Is the water moving, or is the water staying still and something moving inside the water? And it's a bit cold outside, and if I light a fire to get myself warm, why does it make me warm? And what does that mean? What is fire, and what is light? Chemistry deals with chemical things, physics deals with physical things. The fact that chemistry is sort of in between physics and biology is one of the reasons that it's called the central science, because it forms the link between physics below it and all the other sciences above it. As an example, behind medical science is biology, and behind biology is chemistry, and behind chemistry is physics. Or here's another. Behind materials engineering is engineering. Behind engineering is chemistry, and behind chemistry is physics. And again, behind oceanography is, say, environmental science. And behind environmental science is earth science. And behind earth science is chemistry, and behind chemistry is physics. And this would naturally lead one to ask that if chemistry is the central science which is behind all the other sciences, and physics is behind chemistry, then what is behind physics? And the answer is mathematics. You see, the physicist looks behind the layers, behind what we normally see and experience in our everyday life in the universe. They want to describe how nature works using the language of math, a correct math formula that actually describes the physical world. That's the goal anyway, because notice that I said that the formula must actually describe the real world. Because some of the most brilliant scientists in the world discovered that they were able to actually fool themselves with formulas that were technically correct in the blackboard world, but didn't actually work in the real world. This even happened to Einstein. Math formulas only have to be logically true, but the work of the physicist must match with the real world. As the physicist Richard Feynman said, mathematics isn't real, but it feels real. So the physicist tries to make mathematical formulas that are not only beautiful and elegant and simple and logical, but they also have to fit in the real world. That's important. Now, 2,000 years ago, when it was being developed, algebra was the cutting edge of mathematics, and very few people understood it. But today, college-level physics requires years of study to master advanced algebra, as well as inverse functions, simultaneous equations, differential equations, quadratics, exponentials and logs, trigonometry, calculus, and analytical geometry, as well as methods of approximation and probability and statistics. Wow, that's a lot. What if I don't know all of that? Is there any hope for someone who just wants to know some physics to get a better appreciation and understanding of the universe and how it works? Yes, there is. Because the reality is, even though you need to have advanced mathematics to appreciate the complexities of physics, you also need to know how to read music to appreciate the complexities of this symphony. But you do not need to know how to read music to appreciate the beauty, the symmetry, and the majesty of this symphony. You don't even need to play an instrument. Likewise, you do not need to know how to solve a single mathematical equation to better appreciate physics. Once some of your questions are answered and you have a few basic concepts, you will have a better appreciation for the beauty of how the universe is designed, the symmetry and the majesty of creation. This idea of taking the basics of physics first and leaving the heavy math and formulas for later was largely the approach taken by scientists like Michael Faraday and James Clerk Maxwell when they would teach their introductions to these disciplines. They felt that mathematics was certainly useful and necessary, but it was no substitute for clear thinking. The main reason to have an introduction to physics is to enhance your understanding of the physical world and to better appreciate the universe and how it works. And somebody is bound to ask, if behind science is chemistry, and behind chemistry is physics, and behind physics is mathematics, then what's behind mathematics? And one would probably have to say the laws of logic, because it is the laws of logic that allow mathematics to be coherent and even possible. And what's behind the laws of logic? There, as Einstein would have said, is the mind of God. There are definite limits to the territory that physics can cover, and there are limits to what science knows about the natural world. For example, there are at least 3 arenas where the territorial boundaries of science ends. First, science cannot answer questions about morality. Science helps tell us how the world is, but it cannot tell us how the world ought to be. It can help us to make a poison, but it cannot help us to know whether to use the poison or not. That is a moral question. Science deals with the areas of atoms and of motion. It can tell us how a liver works, but it cannot tell you how to behave, or what is good, or what is just, or evil. This is simply not the arena of physics. These are the arenas of metaphysics, of spirituality, and of religion. Likewise, a second area that science cannot help us in, science cannot tell us what is beautiful and lovely or valuable. In short, science cannot answer artistic or aesthetic questions. There is no scientific answer to the question, which of these flowers is prettier? Or, which smells worse, a skunk or a skunk cabbage? This arena is called aesthetics and art. Science can help us do art, mix paints, build canvases, but it cannot tell us what is beautiful and lovely or valuable. The third arena that science cannot help us with is questions about the supernatural. Super is Latin, meaning above or beyond. So supernatural means above or beyond the natural, above physics, above chemistry, above biology, above what we can feel, touch, see, and measure in laboratories. Supernatural. The tools of science only fit around natural questions. They are not designed to fit or to work on supernatural questions. Because the realm of science only works with natural phenomena and explanations, these questions are outside the realm of physics and must be answered by metaphysics. Meta is the Greek version of the Latin super, and it also means above or beyond. Supernatural or metaphysical questions are essential parts of what it means to be human, and science cannot help us in this arena. Notice this does not mean that scientists are excused from the moral issues surrounding their work. Like everyone else, they are morally and ethically accountable for what they do. Every scientist has his or her belief about how the universe began, what is good, what is evil, and why, who is God, what is just, and what is unjust. And they get this information from their faith, or from their religion, and from their spiritual beliefs. They do not get this important information from the laboratory. Those are some of the limits of science's territory, what science can and simply cannot do. There is also a limit to what science knows. You see, it is really easy simply to give something a name and then declare, because we have a name, we understand it. For example, we observe an event, like this cereal falling to the dish every time I release it. But why does it fall? So we take careful measurements of speed and mass and acceleration, and we give the falling event a name: gravity. Gravity is why the cereal falls to the bowl every time. But then someone curious enough will ask, yeah, but what exactly is gravity? And then the answer is, well, it's the thing that makes the cereal fall to the bowl. You see, you haven't actually answered the question. You've simply given it a label. The fact is, we really don't know what gravity is, or where it comes from, or how it's even really produced. So let's take another example from medicine. If you feel sick, your doctor might diagnose that you have an idiopathic illness. Oh, good. You assume because he has a label for it, he understands what is making you sick, until you realize that an idiopathic illness is a word that doctors use for, I have no idea what is making him sick. Idiopathic literally means arising from an unknown cause. Idiopathic pulmonary fibrosis means his lungs are getting stiff and I don't know why. Idiopathic hypersomnia means he's getting really tired during the day, and I don't know why. Just having a buzzword or a label for something is not the same as understanding it. Now, it helps and it moves the discovery process along, but a label should never be confused for an answer. Plus, any answer that you give for gravity or any other occurrence will naturally give rise to more legitimate questions. Why does the rock fall? Why does the orange juice stay in the glass? What is gravity? What is the physical mechanism that causes it? Why does the universe work in this way? At some point, our understanding fails us, and we have to fall back on, well, that's just the way it is. Or, that's just the way God made things. Or, we don't know. Or in the worst case scenario, stop asking questions. Hopefully, none of those are the final answer, and our lack of information and knowledge should prompt further investigation. So what we really mean is, we don't know, but we have some theories that might prove valid. Or, of course, this is the way God did it, but how did he do it? What mechanisms did he employ? So as powerful as science is, we see that there are some arenas that science simply has no jurisdiction in, and we've seen that there are definite limits to what science really knows at any one time. An introduction to physics should teach some of the basic concepts of physics in a friendly, encouraging, and illuminating way, rather than being confusing and intimidating. It should give us the satisfaction that we can, at some level, explain some of the world that we see around us. The physics of things like sound and light and heat and gravity, and even to better understand some of Einstein's own ideas. Because the power of physics is the power to explain. In Physics 101, we will learn the basics by answering many of the questions most often asked by kids and adults about the world around them. For example, when eating breakfast, almost nobody asks, is light a wave or a particle? But almost everybody asks, why is my face upside down in this spoon? And by answering that question, you end up in a much larger discussion about light and mirrors and reflection and refraction. In Physics 101, we divide the physical universe into big categories of light, sound, heat or thermodynamics, electricity and magnetism, motion, physics of the weird, and the future of physics. We begin with light. And in our everyday experience, there is probably nothing so familiar and so obvious as the sky above us. So, in our first physics segment, we will begin by asking one of the most basic questions asked every day by children and adults all over the world. Why is the sky blue?